Okay, so the second is a shortest path algorithm. The shortest path algorithm are essential in graph theory for finding the most efficient route between nodes in a graph, right? So if we want to find the efficient route between our nodes in a graph, we have a different kind of shortest path algorithm. These kind of algorithms are widely used in various applications such as navigation system, network routing, and logistics. And two of the most commonly used shortest path algorithm are Dijkstra algorithm and Bellman-Ford algorithm, right? So these are our most two used or commonly used shortest path algorithm. We are calling it what? Dijkstra algorithm and Bellman-Ford algorithms. So let's see one by one, right? So let's start by Dijkstra algorithms. So, Dijkstra algorithm. The steps for this algorithm: first, we initialize distances from source vertex to all other vertex as infinite, and the distance to the source as 0. So we might have a different kind of vertex in our graph, right? So we set the first vertex as 0 or as our starting point, and we set all other vertex as infinite because we actually know the weight which might be here. So the second is use a priority queue to select the vertex with the smallest distance. Then we use priority queue to select the vertex with the smallest distance. Then update the distance of adjacent vertex based on the edge weight. Then repeat until all vertex are processed. Example of this is the code initialize distance from the start vertex to all other and use a priority queue to explore the shortest path. The graph is defined using a dictionary and the function returns the shortest distance from the starting vertex to all other vertex, right? So Dijkstra algorithm find the shortest path from a single source vertex to all other vertex in a weighted graph with non-negative edge weight, right? So this is a point to note. Dijkstra algorithm find the shortest path from a single source vertex to all other vertices in a weighted graph with non-negative edge weight. Non-negative edge weight. If you have a graph with a non-negative edge weight, then Dijkstra algorithm is not the one to be used, right? So you can use Bellman-Ford algorithm for such kind of scenario. Yeah. Okay, so let's explore this Dijkstra algorithm using Python. So for instance, you have been given this example here, right? So first to input heap q. This heap q means what? Our heap q is the priority queue, right? Yeah, so input a heap queue so as we can define our priority queue. So the first step is initialization, right? Is initialization, whereby we initialize a dictionary called what? Called the distance. So a dictionary called the distance is created initializing all vertex in a graph with equal to infinity, right? So all vertex are equal to infinity. Then we set our start distance equals to 0. Then we define our priority queue equals to 0 and what? And the starting point. So priority queue, which is implemented as a main heap, is initialized with a tuple of starting vertex and its distance. So starting vertex is 0. Distance is what? Distance is start. Then after that, what we do is we are looping for our priority Q. We are looping for our priority queue to continue until the priority queue is empty. So we loop until the priority queue is empty. So within this priority queue, right, within this loop, the vertex with the smallest distance is what? Smallest distance is calculated or is processed. After that, we are exploring every neighbor. So for the current vertex, the algorithm look at its neighbor and calculate the potential new distance to each neighbor. Then we are checking if that potential distance of this neighbor is smaller than the current one. Then we are updating our what? We are updating our queue. How can we find the distance? We are finding the distance by taking the current distance plus the weight in which each neighbor have, right? So if the distance is less than the distance of the neighbor, then we are setting the distance of neighbors equal to the distance which we calculated here, right? So after that, we hit push to our priority queue. So we are updating our what? Our queue, right? Yeah, so that's how it works. So take this example. We have a vertex A which have B with weight 1, C with weight 4. We have B which has a vertex like A with weight 1, C 2. We have C with B 2, D 1, D with C 1. Remember, at the first time we are setting every vertex here, A, B, C, and D equals to infinity. Then we are setting the first distance here equal to 0. So all of this remain with what? Remain with infinity. While A start with what? Start with 0. So we are starting calculating the distance of what? Of each neighbor. So after to calculate the distance of this neighbor, we are taking what? We are taking the current distance. The current distance is what? Is of A plus the weight. So now, if we want to calculate the distance of A to B, we are taking A, which is 0, plus the weight of B, which is 1. And we are getting that B equals to what? B equals to 1. So A is 0, B 1. Then we are calculating for C. C here is what? C here is 4, right? B, A has what? A has 0. So C will remain with what? C will remain with 4. Then we are coming to B. Remember, B now is what? B now is 1, right? Now we have A with an edge weight of what? Edge weight of 1. So if we want to find this distance, we are taking the distance of A, edge weight of A, which is 1 plus A1, which we get what? We get 2. Remember, 2 is greater than whatever we have for A right now. As A is what? A is 0, and we want to find the smallest distance. So we will skip this one as it is greater than what? As it is greater than the current A that we have. Then we are going to C. C now, it has an edge weight of 2, right? But B is 1. So C plus, which is 2 plus 1, we got 3. So C now is 3. But remember, we have already have a C distance, which is what? Which is 4. But 4 is greater than C that we are currently have, which is 3. So we are going to update our C equals to 3. Why? Because 3 is smallest than 4. At this part here, say if distance we are calculating is less than whatever distance that we have currently, then we are taking that distance. Then we are pushing it to our priority queue. So in our priority queue now, we will set C to 3 and not 4. Then we are going to set it to C and D. Also, we are doing the same thing, right? Yeah, so that is our shortest path algorithm using the Dijkstra algorithm. Second is Bellman-Ford algorithms, right? So in Bellman-Ford algorithms, we initialize distance from source vertex to all other vertices as infinite, and the distance to the source as what? As 0. Same to the Dijkstra algorithms, right? Yeah. Then for each vertex, relax all edges. So we are applying the relaxation mechanism, updating the distance to the adjacent vertex if a shorter path is found. Then we are repeating this process for a total of V minus 1. V is a number of what? Number of vertex. So number of vertex minus 1 iteration. So V is the number of vertex. Then we check for negative cycle by attempting to relax the edge again. If the distance can still be updated, a negative cycle exists. So explanation to this is the Bellman-Ford algorithm also initializes the distance of all vertices to infinity except for the source vertex. So it relaxes all edges repeatedly to ensure that the shortest paths are found even when negative weights are present. So after that, it checks for negative cycle, which can lead to an infinite reduction in the path length. So we can say that the Bellman-Ford algorithm is used to find the shortest path from a single source vertex to all other vertices in a weighted graph, accommodating negative edge weight. While the Dijkstra algorithm can't accommodate a negative edge weight, the Bellman-Ford algorithm can accommodate a negative edge weight. However, it can't handle graph with a negative cycle. So we can say that a Bellman-Ford algorithm is another method for finding the shortest path from a single source vertex to all other vertices in a weighted graph. But unlike Dijkstra algorithm, it can handle graph with a negative edge weight, right? So that is Dijkstra algorithms. So let's take an example for this. So for instance, we have this kind of what? This kind of graph. A, B1, C4, B, C, minus 3, D2, C, D2, D. So at first it will make every of these vertex to infinite except for the first vertex A, which will be 2 equals to 0, right? Then it will start exploring each neighbor. So it will explore 1, we'll get B is equal to 1. It explores C, we'll get C equal to what? C equal to 4. Then it will go to the vertex B. It will see C. B is what? B is 1. C is negative 3, right? So we got 1 plus negative 3, which will get C equals to negative 2. Then it will go to D, which is 2. B is 1. Then 2 plus 1, we got D equals to how much? We got D equals to 3. Then to C, D is 2, right? So C is how much? C is negative 3. Negative 3 plus 2, we get how much? We get negative 1. Then D is empty. So that is Bellman-Ford algorithm. It will do this thing for the first iteration, second iteration, and the third iteration. Why 3 iteration? Because we are relaxing edge up to V minus 1 times. So if we have a 4 vertex, means we will iterate third or 3 times. So that is Bellman-Ford algorithm. So it will do for the first time, it will do the second time, it will do for the third time. If nothing change, then we will print our Bellman-Ford algorithm graph, right? Yeah. So we also have a minimum spanning tree. A minimum spanning tree of a connected or unrelated graph is a subset of the edge that connect all vertices together without any cycle and with the minimum possible total edge weight. So what it does is it connects every edge, right? Every vertex together with every edge from it, and then calculating every edge totals. If it's get every edge totals, the one with the most minimum possible edge weight is what we are saying, right? So we are saying that minimum spanning tree is a subset of edge that connect all vertices together without any cycle and with the minimum possible total edge weight. That's the output. We need to find the minimum possible total edge weight. The most popular Kruskal algorithm and the Prim's algorithms, right? So that's 2 popular algorithms. So the first one is a Kruskal algorithm. So algorithm steps are sort all edge in a decreasing order, then initialize an empty tree for MST, add edge to MST by considering the smallest edge first, ensuring that no cycle are formed using a union find data structure to check for each cycle. Then stop when there are V minus 1 edge in MST, where V is the number of vertices, right? So we are saying that Kruskal algorithm is a greedy algorithm that finds the MST by sorting all edge and adding them one by one to the MST, provided that they do not form the cycle, right? Yeah. So the second one is Prim's algorithms. So in a Prim algorithm, the steps are initializing the MOST with a single starting vertex, then maintain a priority queue of edges that connect the MOST to the rest of the graph. So while there are vertices not in the MOST, are the smallest edge from the priority queue that connect a vertex in the MOST to a vertex outside of it. Repeat until all vertices are included in MOST. Or we can say that Prim algorithm are used to find the minimum spanning tree of a connected graph. So the MOST connect all the vertices with the minimum total edge weight without forming any cycle, right? So we can say that Prim algorithm is another grid algorithm that builds the MOST by starting from an arbitrary vertex and expanding the tree by adding the minimum weight edge that connect a vertex in the tree to the vertex outside the tree. So that are Prim's algorithm. So for instance, here we have a code where import heapq. This means that we are importing the module of heapq, which will allow us to use priority queue. This is helpful for efficient retrieving the smallest edge weight. Then we are defining the function called prim, which take two parameters. We take a graph and start. The graph adjacent list of the graph and start the starting vertex for building our MOST, right? Then we are initializing three variables. The first one is MOST, the second one is visited, and our minimum heap, right? So our MOST will store the edge including in the minimum spanning tree or including our MOST. Visited, which is a set to keep track of which vertex has been included in MOST. And we have a minimum heap, which is a priority queue, which are used to initialize the starting vertex, and a weight of 0, meaning we start from where there is no cost, right? So as you see, minimum height has 0 and start means that we are starting vertex and a weight of what? Weight of 0. Then we are going to our min heap. So while min heap means that we have a loop. So this loop will continue as long as there are some edges to process in our min heap or our priority heap queue, right? Then we will go to extract the minimum edge. So we'll extract the minimum edge. So the heap pop, what it does is, this heap pop, what does it retrieve and remove the edge with the smallest weight from the priority queue. So we have a weight, right? This one, we have a weight, and we have a u. Weight is the weight of the edge, and u is the vertex connected by this what? This edge. Then we are checking if vertex is visited. So we are saying that if u not in visited, it means that if our vertex here is not visited, then we add vertex to our MOST. So if u hasn't been visited, add it to the visited set. Then append the edge which take a weight and u to the MOST. And we are saying that for every v of vertex u, right? For every v of vertex u and w of vertex u. So these loops go through each neighbors of v of vertex u, where w is what? Is the weight of our edge connecting v and what? V to u. How we can say u to v. Then we add unvisited neighbor to the minimum heap using what? Heap push. So all the visited neighbor will be added to our min heap or priority queue heap. Okay. After that, we return what? We return MOST, or we return our result. So the function returned the MOST excluding the initial 0 weight edge added at the first start. So as you see here, exclude initial 0 weight edge. So let's take this an example. Here we have vertex A connect to vertex 1 with a weight of 10, right? So vertex, this vertex 0 connect to vertex 1 with a weight of 10. Also vertex 0 connect to 2 with a weight of 6. Also 0 connect to 3 with weight of what? With weight of 5, right? So let's see how the execution is going. So first, after initializing everything, we are doing our first iteration, right? So visit vertex 0, that's the first thing we do, right? So after visiting the vertex 0, add visited equals to 0. So we add 0 to 0, right, to MST. Then we are going to the neighbor of zeros. Neighbor of zeros are 1, 2, and what? 1, 2, and 3. 1 with 10, 2 with 6, and 3 with what? With 3 and 5. Then we are adding weight, which is 10 to 1, 6 to 2, 5 to 3, and go on until we iterate through every neighbor in our in our graph. So that's how our prime algorithms works. So you have been given an activities where you are tasked with calculating the numbers of ways to climb a staircase with n step, where you can take either 1 step or 2 steps at a time. So let's have function n be the number of ways to climb the n step. The relation can be defined as this one: fn minus 1 plus fn minus 2 for this one. So the question what is the base case for this recurrence relation, right? The first 5 terms of the sequence defined by this recursive relation. Then using the recurrence relation, calculate the number of ways to climb a staircase with 5 steps. After that, what is the time complexity of solving this recurrence relation using a recursive approach? So it takes your time, analyze the problem, design the algorithm, and implement the algorithm by answering these kind of questions, right? So it takes your time by doing this kind of activity, right? So that's it. So, and this is activity feedback. You can read it by yourself, whereby the question, the question 1 answer is the base case f0s, f0 which is equal to 1, and f1 which is equal to 1, f1, and this one. So the question 2, the first 5 terms will be this one, and this one. Question 3, the same. The question 4, the time complexity of solving this recurrence relation using an IV recursive approach is 0, big 0 quadratic n, because it results in a binary tree of recursive calls. So this marks to the end of this lesson. See you in the next lesson, where we will learn about searching and sorting algorithm. So see you in the next session, and take your time by reading this well and clear. See you in the next session. Thank you.